It's a lot of fun to be at the second HLAI conference, and I think it's the 11th AGI conference, something like that. So we started with the AGI workshop in 2006. And then 2007 we skipped, 2008 we started the first official AGI conference, and I think BICA started maybe a year or two after that or something. So it's been a while, and obviously there's been a big change in the mood of these events. I mean, in 2006, it wasn't exactly that we were like gathering in a basement under threat from the police or something. I mean, we were in the conference room in a Marriott in Bethesda. It wasn't that romantic, but still, it was like 50 crazy mavericks who were, meeting outside of what was the norm of academia or industry at that time. And we're talking about how to build thinking machines that can really think like people and ultimately much better than people. And this was a sort of thing that you didn't really talk about much at an academic AI conference. You talked about it, over a beer afterwards, but not in the sessions. And in major companies also, you weren't paid officially to work on that. You might do it in your spare time. And that obviously the situation is different now. Major corporations are taking AGI as part of their business model and their strategic plan, and you can now be taken seriously in major universities working on things related to human-level AI and general intelligence. I mean, it's still the case that the tremendous majority of AI work in academia is narrowly specialized and focused on application of AI to very special areas or on very particular algorithms that would seem not to have great potential for general intelligence. And certainly it's still the case that the vast majority of AI work in industry is focused on solving highly specific problems. But nevertheless, the atmosphere has certainly changed tremendously, and I think this is certainly a good thing. It's also led to confusion of various sorts. I mean, since AGI has become more popular, it's now become to some extent a marketing slogan. So things that maybe I wouldn't, or some of you wouldn't consider really AGI focused are using that name now because it sounds cool. And of course, since any two researchers are bound to have slightly different definitions and concepts of what AGI is, it's hard to really crack down on that, because if we can't agree among ourselves on exactly what AGI is, how can you condemn some company for saying what they're doing is sort of on the way to AGI? So there's, in some ways, more confusion now, but nevertheless, I think we're in a much more positive time for general intelligence than we were when we started the AGI and BICA conference series 10, 12 years ago. But I think it's really just beginning. So we've seen a revolution in narrow AI in industry in the last few years, and I think we're going to see the general intelligence revolution in, let's say, the next 3 to 10 years. I think we're going to see AGI grow from here tremendously more than it's grown in the last 12 years. And just as deep learning has started to do popular things that are making people a lot of money and getting everyone's attention, and this has driven some virtuous cycles in terms of resources and enthusiasm and attention, we can see the same thing from AGI. So I think this is it's an incredibly exciting time to be in the field. And of course, AGI is a very big topic. I'm not going to try to cover all of my thoughts about it here. I'm going to review rather one aspect and then a few different ramifications of it, which is the complex self-organizing network aspect of AGI. So one view of AGI is that we can approach it by looking at complex networks of complex networks, and we can take an integrative approach where you're taking different AI algorithms or modules and connecting them together, and then you can look at different modes of integrating things, like how tightly do you integrate them, how closely, or can they be loosely integrated, and hierarchies of integrated systems within integrated systems within integrated systems. And I'm going to take this perspective to review various of the things I'm involved with now, from the OpenCog general intelligence architecture to the Hanson AI software underlying the Hanson robots, and then the SingularityNET blockchain-based AI marketplace. So that's OpenCog, Hanson Robotics, and SingularityNET are three different projects, and they do link together on the software level, as well as having some of the same people involved with it, but they also have in common an integrative view of general intelligence, that perhaps you can get general intelligence to come about as a result of the emergent activity of different AI modules connected together. So for this audience, I don't need to go through much about narrow AI versus general AI. I mean, what we're talking about is AIs that can generalize well beyond their original programming or training data. And you know, I tend to agree with Marcus Hutter and so forth that totally general AI may not be possible without infinitely much energetic or computing resources. But nevertheless, there's a strong sense in which everyone in this room is a more general AI than AlphaGo or Mathematica or the current version of OpenCog, right? And in that sense, it also seems clear human beings are not the most general possible AIs. So we're looking for something that can generalize to deal with domains that its programmers and its training data suppliers hadn't ever dreamed of, by doing, you know, analogy, induction, abduction, and making creative leaps beyond what it's seen before. I mean, as a standard example, a generally intelligent self-driving car system will be able to adapt to learn to drive a truck or a motorcycle. And if a bunch of dinosaurs escaped from Jurassic Park and romped across the highway, even though they weren't in its training data set, it would realize it probably shouldn't drive into them, right? And that's not where we are now with narrow AI self-driving car software. So I've been approaching AGI. Haven't gotten to human level AGI yet, and nor has anyone else, but I've been approaching it for a while via the OpenCog approach, which you could read about in these books mentioned here. And we're also using OpenCog to help control the Hanson robots in what we call the whole organism architecture for Hanson Robotics. And we're embedding it with other AIs in a larger network in the SingularityNET framework. And I'm gonna talk about all of these things, different ways of integrating multiple AIs together into complex networks. So before launching into AI, I want to talk a little bit about integration and what I mean by tight versus loose integration. And because we can see different levels of integration of components in nature as well as in engineered systems. So this diagram, each radial axis, each little box there is a region of the brain as identified by neuroscientists. Each region has many, many different functions, some of which are known, some of which are not yet known. The lines indicate connectivity of brain regions to each other. So it's not a wiring diagram of neurons, it's a connectivity diagram of brain regions, right, where most complex functions occur with networks of many regions connecting to each other. But these different regions of the brain, like say the thalamus, cortex, basal ganglia, they're quite tightly interconnected, and if you remove one, the others are going to stop doing some of the things that they were supposed to do. So this is a pretty tight integration of brain subsystems, and certainly, as another point, this drives home the complexity of what's going on in our heads as opposed to, say, a convolutional neural network or a Hopfield net or something, because each of these modules of the brain has its own architecture, its own mix of neuron types, its own mix of neurotransmitters, and they're doing their own type of computing or dynamics, and they're connected together in a certain way. Now, the systems of the human body are also integrated together pretty tightly. I mean, there's an endocrine system, there's chemical signaling, there's even biophotonic signaling, there's a lot of stuff going on, but they're not quite as tightly connected together as regions in in the brain are. So it's a slightly looser connectivity, and then all of us connected together in society, forming a sort of global brain, as some have called it. That's a yet looser integration, but highly critical, right? That's culture, which is responsible for our ability to talk about all these things now. That comes from the interconnection of all of us. So what we have here is a hierarchy of a very tightly integrated system, less tightly integrated, and even more loosely integrated system. And I think this one can look at in AI as well. So just speaking very broadly, we look in human intelligence, we have the brain, the body, and society. In my own AI universe, and one could draw other analogies with other AI systems, OpenCog is a tight integration of different algorithms. I'll talk a little more about that momentarily. We're connecting OpenCog with other computer vision, movement, audition algorithms in the Hanson AI framework, and that's a bit of a looser integration, controlling different parts of a robot body. And then in SingularityNET, we're making an even looser integration, which is really more like a society or economy of minds, where you could have totally different AIs all connected together and cooperating. And this sort of thing is complex, right? With the networks within networks within networks with different levels of integration. And I think this is the sort of way that intelligence comes out of biological systems. It's not like there's one chemical or electromechanical trick, which is the magic formula of intelligence, like 1 sodium plus 2 potassium minus 3 acetylcholine going through this channel or something. I mean, it's more about the self-organizing dynamics in hierarchies of systems. So in OpenCog, as the example of tight integration I want to talk about, we have a knowledge representation most of you have probably heard me say something about before, which is a weighted labeled hypergraph called the atom space. And we chose this representation because it's a reasonably convenient way where you could represent programs, you could represent logic expressions, you could represent neural networks, and all these things with only modest awkwardness can be represented in the same weighted labeled hypergraph. I mean, it's far from the only universal representation out there, but it seemed to be one that wasn't insanely inconvenient for any one of the representations that we need to do in AI. I mean, this is just a random screenshot from the visualizer we used to actually look at the OpenCog atom space, which is showing some stuff from parsing a sentence. And we try to handle every type of knowledge that cognitive scientists identify as being in the human mind. Declarative knowledge, which is acted on by a probabilistic logic engine, PLN, and we have the primary developer of that, Noel Geisweiler, sitting in here. And then attentional knowledge, like focus of attention, which we'll have a talk about in the BICA conference in about an hour. Procedural knowledge, which we handle, among other methods, by evolutionary learning. Sensory motor knowledge we handle now by integrating deep neural networks with this hypergraph. So with a common hypergraph representation, we try to have many different algorithms work together on a common representational store, it's analogous to what was called a blackboard architecture in the 1970s, except our algorithms are more powerful and scalable, and our blackboard isn't a bunch of simple propositional logic relations. It's this weighted labeled hypergraph with a more representational complexity to it. But the point I want to make here is what we're doing is we're tuning specific algorithms to work really tightly together, like to get the PLN logic engine to work together with the attention allocation software, which is economic attention networks. I mean, we do a lot of work to make these things operate together and tune the parameters of each one and make the representation of one work with the other one. So we're very tightly integrating different algorithms doing different things, and that's a lot of work. I mean, integrating the two algorithms can be as much work as inventing an algorithm. And I think this kind of tight integration is necessary if you don't have multiple AI algorithms that can understand each other's intermediate representations. So I mean, if PLN logic reasoning gets stuck and wants help, it's got to be able to pass its intermediate knowledge state to some other learning algorithm for help. And if you want that level of interoperation between algorithms, they need to be quite tightly integrated. It's like people who are so closely working together, they can understand each other's like half-baked, inarticulate trains of thought and help each other out. That requires very, very, very close interaction. So we have evolutionary learning, logic, neural network, other search algorithms, but they're integrated together on a common representation so they can all help each other. And of course, just integrating a bunch of algorithms isn't enough. In OpenCog, we're doing this in a system based on what I think of as an observation-based semantics or experience-based semantics. So you're creating a system that observes data from the world and then tries to give meaning to abstract concepts by grounding them in its observations, but it does this using a bunch of different tightly integrated together learning algorithms. We're developing this with a view toward general intelligence. We're also using it, as I'll talk about in a few minutes, for some robotics applications in Hanson Robotics with Sophia and other robots, and some biology applications to reason about genetic and proteomic data. And there'll be a couple talks in this conference from this line of work. So Ms. Gana Bieta is giving a talk in the session, in the BICA session after this, on the attention allocation module of OpenCog, sort of showing how attention shifts when an OpenCog system is reading text, and how it comes up with new ideas by indirectly extrapolating what it read. Like if it read some articles about insects and read some articles about poison, it'll think about insecticide just by sort of spreading of attention. Anton Kolonen will give a talk on some work we've done with OpenCog and unsupervised language learning, so inducing grammar just from a big corpus of text without any labeled examples, just by pattern mining, learning grammar. And Alexei Potapov will talk about some work integrating deep neural networks with the OpenCog to work toward cognitive computer vision. So these are each pieces of the OpenCog paradigm, and they each involve integrating together different components in different ways. I mean, it's clear in the integration of neural nets with symbolic reasoning, but also our unsupervised language learning approach. We use sub-symbolic approach for dimension embedding to drive word sense disambiguation and part of speech learning, but we use symbolic reasoning in the hypergraph for parsing. So there's a mix of different algorithms in each of these applications. Now, taking a level up, in Hanson Robotics, we have OpenCog, but we also have a bunch of more specialized tools to deal with navigation, with perception from the robot eyes, with auditory perception and signal separation, with speech synthesis. And these tools are integrated together. They use ROS, Robot Operating System, but they're integrated together more loosely than the different components within OpenCog. Like they don't have to all write dynamically on the same hypergraph. They could use different representations if they want to. And I look at this roughly as being analogous to the way organs in the body are integrated, which is not as tight as the way regions in the brain are integrated. And I'll talk a little more about Hanson Robotics in a few minutes. And then SingularityNET project. So this is something more recent, which we launched, I guess, about a year ago, although progress accelerated when we raised funding for the project in December. And this is even looser coordination, because this is a platform where anyone can create an AI. They can put an AI into this blockchain-based framework. It will then talk to the other AIs in the network. And you can have federations of AIs cooperate to solve problems, even if they were written by different people, and the algorithms inside them may be opaque and proprietary. As long as they communicate according to the specified APIs, they can coordinate into overall federations and networks. So here, again, we have a hierarchy of integrated systems, with OpenCog very tightly integrated, the components of the Hanson robot more loosely integrated, and the AI agents in the SingularityNet even more loosely integrated. So this it's a big and complicated perspective, which is part of the reason it has taken a while. So and the top picture, I think my oldest son is in the middle there, and I remember he was following me around when he was quite young, and I was working on AI already back then. When he was 10 years old, he told me if I didn't finish creating a superhuman AI by the time he was 18, he was going to take matters into his own hands and finish it for me. So he forgot that. But once he turned 18, I started harassing him about it constantly. And finally he went to grad school for AI just a couple of years ago, and he's actually studying at this university in I guess electrical engineering department. But what he's doing is not very electrical, except it uses computers. It's machine learning applied to automated theorem proving, and his advisor Joseph Erbaum will give a talk in this conference. But now I've produced another human biocomputer, which is Goertzel in the bottom, and so the question is, will we succeed to create AGI before this guy grows up? I mean, I failed totally before my first kid grew up. I mean, you create these biological computers, and they just kind of grow and get smarter and smarter year on year if you keep feeding them and don't torture them too badly. But yeah, creating the digital one is a lot more trouble. But we gave him an AI-oriented name just to kick things along. So the first name, Goertzel, is an acronym for Quantum Organized Rational Expanding Intelligence, which is a fault of my wife, Ray Ting. And then the middle name is named after ICSI, which is Marcus Hutter's infinitely intelligent but impossible AI algorithm. So we figure with these names, if we haven't created the super AI by the time he grows up, he's like, he's culturally destined to finish it for us. So, but hopefully we'll finish before he even understands what I'm talking about. And I think there's a lot of different pieces, but it's going to have to be a complex network, or in this case, a network of networks of networks. And that doesn't mean there's not hardcore algorithmic problems to solve at various levels of this network, which I'll talk about. What it means is that it's not just make one algorithm, and the one algorithm will do everything for you. So within this general framework, I'm now going to go through a few specific topics, ending up with the Hanson Robotics and SingularityNET. So I want to talk quite briefly about how deep learning fits into this perspective. And first thing I'd like to do is put it in the perspective of neuroscience. So remember my big picture of all the different regions of the brain. If you look at CNNs and related architectures for vision processing, these are best considered a very crude model of the mostly feed-forward activity of a few different regions of the human brain, which is in the vision processing pathways. And I mean, it's interesting. We're still not modeling most of the feedback activity there, from cognition down to perception, but it's fascinating to roughly model these type of the brain and these parts of the brain, and then improvise off that to make better and better algorithms. But we're also not taking inspiration from all the other parts of the brain in this type of architecture. And of course, there are some people going beyond that. If you look at like differential neural computers, neural Turing machines, and so forth from DeepMind, they're bringing in models of hippocampus and other parts of the brain into this story. So there's some attempts to go beyond this, but it's worth remembering that this sort of feed-forward hierarchical pattern recognition, so far as we know, is not everything the brain does. It's what some particular subnetworks within the brain do. So what we're doing in OpenCog in our use of deep neural nets is basically hybridizing a deep neural net with a more abstract representation. And clearly that's not exactly what the brain does, right? I mean, we're taking the deep neural nets to model some sorts of perception recognition, perception operation, and then we're using more symbolic methods like our probabilistic logic engine to model abstraction and conceptual thinking, whereas the brain uses some other sort of neurally implemented representation algorithm to do abstract thinking. But one of our research goals in playing with neural nets in this way is to try to get neural nets that internally have a sort of sensible semantic model of what they're looking at. And there's a bunch of other people working on this now too, sort of representationally transparent neural networks. And this is really useful if you're trying to integrate the neural net with a logic engine, because then the logic engine could look at the internal representations of the neural network and do pattern recognition and reasoning on them, rather than just, say, looking at a classification judgment that it made. And I don't have time to talk much about this now, but if you look at the SingularityNET blog, there's a post from Alexei Polipov, who leads our SingularityNet St. Petersburg team, on Deep Semantic Net to be bridged for SingularityNet. So he doesn't claim we've bridged it yet, but we've done some preliminary work in that direction, which he's talking about in his paper here at the AGI conference. In the blog post, he speculates a little further. So we're taking perception from neural nets, and we're plugging them into OpenCog's pattern matcher and trying to get the symbolic pattern mining and the sub-symbolic pattern recognition to work together. But to get that to really work as well as we'd like, we need to make more progress on the level of deep neural nets that have a semantically transparent representation that a logic engine can make sense of. What I personally think is the biggest algorithmic leap we need to make to get to general intelligence is what this guy Neil Geisweiler there is working on. So no one murder him. We really need him to. I mean, apart from the fact he's a really nice guy, we also need him to finish the AGI for us. So adaptive inference control. So I think you could make an AGI in a purely sub-symbolic way. I don't see why not. On the other hand, I think we're going to do a better job using an explicit probabilistic logic engine as a core component. You're going to get an AI that can do abstract reasoning faster and better and less insanely and more rationally than something that grounds its reasoning in the more easily implementable neural type operations. And we have a logic framework called PLN. There's been a lot more recent stuff written about it than this book, which has some obsolete things in it. But the PLN in its current form, just like every other logic system, has an Achilles heel, which is the control problem, a combinatorial explosion problem. So you can have a nice logic which lets your system draw conclusions from premises, and we can take probability distributions attached to premises and propagate them through to conclusions, and you can reason about perceptual data or movements, not just abstract mathematical or linguistic stuff. On the other hand, if the problem of choosing what logical premises and what logical axioms to apply in what order is intractable, then it doesn't matter how nice it is in theory. Jürgen Schmidtjer with the Goertzel machine basically gave a decent semi-rigorous argument that a theorem prover could achieve massively superhuman general intelligence, but the Goertzel machine is not like a practically tractable algorithm, right? And PLN, our logic engine at this stage, also takes way too long to do complex inferences, because if you have as your premises all the data observed by an OpenCog system and going around the world, and then you need to draw logical conclusions from that or do inferences based on that, there's so many possible inferences to do, right? So what Neil has been working on, together with myself and a few others, is adaptive inference control. So making a system that learns what logical steps to do in what order by experience. So the system does a whole lot of different inferences, and it looks over all these inferences at what chains of logical reasoning steps worked and what chains of logical reasoning steps didn't work. It tries to learn patterns in which chains of logical reasoning steps worked well in what context, and then use those patterns to guide its choice of new logical reasoning steps the next time. And of course, this can recurse, right? Because recognizing patterns in your history of past inferences is best done with inductive and abductive reasoning as your pattern recognition algorithm. So then you're using a base case of a simple pattern recognition engine to look at dumb patterns in the corpus of past inferences, and then you're accelerating that by using your inference engine to infer about patterns that occurred in prior reasoning examples. And we've been talking about this for like the 10 years or more that I've been working with NIL. Now this year, we're actually doing it. The logic engine works well enough, and we're applying simple pattern mining to inferences to learn sequences of reasoning steps that are effective and others that are less effective. So we're getting started with the real work of this now, but we're certainly at an early stage here, which we think of as inference meta learning. But Nil wrote a blog post that touches on this and links to some of the code on the SingularityNET blog, introspective reasoning in the OpenCog framework. But yeah, if I had to make a bet of like what is the core algorithm problem that has to be solved in a sort of computer science-y way to get to AGI, this would be it. And of course, this is premised on the fact I think probabilistic logic is a promising approach. But having said that, I want to be clear, like, I don't think you solve this algorithm problem and then that's it, you have an AGI. I mean, the complex network of networks is a real thing. It's just to power that, you need the right algorithms inside it also. And I mean, that's, of course, similar in biological systems. We have this complex network of networks of, neurons and brain modules and organs and people. On the other hand, yeah, you need long-term potentiation to work on the synapses, right? Or else that whole complex system in the brain isn't going to learn and adapt and do its thing. So you need the right algorithms in there, but you need the algorithms to be arranged in the right network of networks. And as a practical application of this, as well as just pushing toward AGI, we're working with a startup called Moza Health, based in Hong Kong and Shenzhen, on applying this reasoning engine to reasoning about biology data, which is an interesting case because you have quantitative data, you have textual information and research abstracts, you have structured data in biontologies. So it's an interesting test case for this work. What I'd really like to do is apply it to automated math theorem proving, but we'll do that after we've gotten a little further in conquering biology because it's more difficult. So the next level up in terms of integration, the slightly looser integration I mentioned, was the Hanson robotics architecture. And let me talk a little bit about that. I had some videos to show. I think I won't show all of them because of lack of time. But I've been working with David Hanson since, I guess, 2013 or 14 now on supplying AI to his funky humanoid robots. And we have in the audience a number of people from the Hanson AI team, I guess Ralph Manhin, Fabian Andres, and Miss Ghana maybe somewhere, who've been working for, some of them, a number of years on applying OpenCog architecture to the Hanson robots. And late last year, early this year, we finally got OpenCog running like fast enough and stably enough that we can use it sometimes as the control system for Sophia, which has been more of a system stability and integration milestone than an AGI milestone so far. But it's been cool. And among the applications we've been doing is we've been working with someone called Julia Mossbridge, based in California, to use the Sophia robot as a sort of a meditation assistant. So I think I didn't bother to connect sound here, which is just fine. I don't have time to show the videos anyway. Let's see. Hold on a moment.
Really notice how it feels.
So in these trials, you have the robot sitting across the table from a human, staring in their eyes, mirroring their facial expressions, and basically leading the person through some meditation exercises. So I'm not going to have time to run through too much of it here, but this...
And you can also...
This was an example from a trial done in California recently. Now, each session is 25 minutes, and watching people meditate for 25 minutes, even with a robot instructor, is not the most exciting thing in the world to do, but these trials were quite interesting because the robot got people to open up their heart and tell some of the deepest problems they were going through, and many people, by no means all, but a significant subset of the people really felt they could get into a deep trance state while meditating with the robot, and some of them said they'd tried to do that with a human meditation teacher and meditation group and couldn't do it, but with the robot meditation coach they were able to. And this is interesting. It's not really about AGI directly, it's about human-robot interaction. On the other hand, if you think about it, if you want your AI to really understand humanity and human culture and values and interoperate in the human world, being able to connect closely to people is really important. And so this is one practical application that's really about having your AI and your robot connect closely to people on like the deepest emotional mind and body level. So I think it's quite interesting to have that in the mix along with the theorem proving and molecular biology and so forth. And in terms of integration, I mean, we're integrating vision, movement, speech, face recognition with the OpenCog cognition engine, but then you're also getting an integration of the human and the robot, and the person nodding and the robot nodding, and eye contact, and matching the tone of voice, and arousal level of the person. So you're embedding the mind-body network of the robot with the mind-body network of the person, which is pretty interesting. And so we tried to make a scientific study of this and gave some questionnaires before and after. We measured heart rate variability. We used deep neural nets to measure the person's facial expression through the experiment, and pretty significantly found that people got more relaxed, they got happier, and they felt more loved after this experience. So we're basically showing that interacting with the robot in this way is a good thing. And I think it's valuable to have applications like this out there, as well as robocops and advertising engines and surveillance networks. But I think it's interesting from an AGI point of view in terms of what kind of data you're getting and what kind of actions your AI is taking. We've also tried some of these interactions with just an avatar, which can work reasonably well, although audio only doesn't seem to work well. We're working with legs and hands, although most of our work so far has just been with the head and voice and so forth. And we're also working on using neural networks to make the facial expressions more realistic, where you model a person's face, you capture using motion capture, either using a depth camera or a regular camera from different perspectives. Then you train a generative model based on the data from motion capture. You can generate new movements there. So this is not as core to AGI, in my personal view, as something like inference meta-learning. On the other hand, it's part of the slightly looser network of integrated systems. And of course, our heart or our medulla oblongata is not as key to AGI as parts of our cortex, but if they're not there, we're not going to be doing intelligent things. So I think all the different parts of the system are useful. And now finally, I want to turn to the most loose level of integration in my hierarchy. We started with OpenCog, which very tightly connects different algorithms together in a common knowledge representation. Then went to Hanson Robotics, where you have AI doing vision, doing facial expression mirroring, doing movement, connected with AI doing language and reasoning in a looser network. Now, the loosest level of integration I'm working on is the Singularity Net Platform, and this comes from a bit of a different place. I mean, on the simplest level, SingularityNet can be thought of as like an app store for AIs. It's a marketplace, but it's what they call a DApp store, a decentralized app store. So it doesn't have to run on any one centralized computer system. It could run all over the place, just like Ethereum and Bitcoin do. So it's a decentralized app store where anyone can put an AI into this network. Then if someone wants AI services, they would ask the discovery mechanism to find AIs that can provide the service they requested anywhere on the network. And the neat thing is the different AIs can outsource work to each other. So as well as an end user who has a website that needs image classification or question answering, they can put a request into that network instead of making an API call into AWS or Google Cloud or Tencent Cloud. But the AIs in the network can also outsource work to each other and ask questions of each other and pose tasks to each other. And that's what makes it a sort of interesting network. So we have a bunch of AI algorithms which can run on a variety of different infrastructures. So the current alpha is running on Ethereum blockchain, but the AI agents view the blockchain through an infrastructure abstraction layer. So it could be moved to any blockchain or blockchain-like layer later on if we want to. And then of course AI algorithms are kind of basic, so you can have agents running, say, open-cog reasoning or convolutional neural net or evolutionary learning. Then you can have AI agents that package these up in vertical market-specific services, say doing biodata analysis or English language question answering or something. And then there's a custom cryptographic token, the AGI token, which is used for payment among the agents in the network, making it an economy as well as society of mind. So the end user could pay with dollars or euros or whatever, but behind the scenes, it's converted into the AGI token, and between AIs, it's the AGI token that's used. So here, yeah, we can look at many different layers. There's the protocol layer where each agent in the network has a certain identity. Each agent has a reputation using a reputation system, which is designed in large part by Anton Kolonen, who's written a bunch of that, which you can find in SingularityNET blog. And then the reputation system allows the network to operate in a decentralized way without the sort of global police force, because if an agent gives bad answers or rips people off, it will get downgraded rapidly, and then people will pay a little bit more to get an agent which has a high rating, and there's a use for machine learning and probably ultimately AGI and stopping collections of agents from gaming the reputation system. But these aspects of identity management and reputation management, as well as things like, bringing back up an agent that crashed. These things live on the underlying infrastructure layer. Then for two agents to talk to each other, there's a very basic API where two AIs say, hey, I have this ID, I have that ID, I have this reputation, I have that reputation. Now let's talk according to English Language NLP API version 7.3 or Video Recognition API number 12. And then once that basic API of APIs has established what specific API the agents want to use to talk to each other, then they can exchange data and requests. And all that detailed and expensive stuff occurs off-chain, not in a blockchain, because blockchains are quite expensive. We're just using the blockchain for managing identity, reputation, and encryption, basically. So the API of APIs occurs within the blockchain layer, but then once you know what detailed API you're using to exchange data and requests, that can occur on the side chain where only the needed results are packaged up and later put back into the main blockchain. And it's interesting, if you think about it in terms of Marvin Minsky's concept of a society of minds, Minsky famously viewed the human mind as a sort of society of agents, and I never quite liked that point of view fully, because I think the human brain is more tightly integrated than human society is. It didn't seem quite right. Like where's the hypothalamus of society, right? I mean, there's no like 60 hertz oscillation binding together all humans in phase like there is in a brain. It seems like there's just more tight integration in the brain than in a society. On the other hand, something like SingularityNET goes beyond a society of minds to an economy of minds. And that's interesting not only from a business model view, it's interesting because the use of money and reputation in this network is an approach to the assignment of credit problem, because of course an economy is a way of assigning credit and value. So by making your society of minds an economy of minds where agents are paying each other for stuff and rating each other on how well they did stuff, you're then letting agents sort of form into networks and federations of mutual demonstrated value. And so the cognitive problem of assignment of credit potentially is solved by the actual economy of agents paying each other for work. And this is very much in the spirit of Eric Baum, who used to come to the AGI conferences. I haven't seen him for a while. His book, What is Thought, explored very deeply the analogs between assignment of credit in economies and assignment of credit in minds. And yeah, there's a lot of interesting stuff there as well when you put OpenCog agents into the Singularity Net, because OpenCog, for allocating attention, uses something called ECAM, which is an economic attention network. So it's sort of like an attractor neural net, but it's spreading around little tokens of artificial money, which are conserved. So in that case, you have a little economy of attention inside each OpenCog, and you also have an economy among different OpenCog agents in Singularity Net exchanging tokens. But the fact that they're all conserved monetary quantities means it helps the integration to work nicely. So there's actually some subtlety here to do with the way money doesn't leak credit and helps with the assignment of credit problem. And if you look at Eric Baum's book, What is Thought, he says a lot about that. So the use of a cryptographic token, I mean, it has a lot of different values here, but one of the values is allowing a monetary approach to the assignment of credit problem among all these different agents. And I'll go through the rest of this pretty rapidly as I have 6 minutes and 26 seconds left. Key idea here is that the AI agents can outsource work to each other, and that's what makes it a complex network. So you could have one AI agent doing video analysis, one doing voice analysis, one doing like semantic information extraction, and in different cases they could each outsource work to each other depending on what they were doing. And this is interesting. It's what makes it more than an app store, because the different apps in the Android Play Store don't typically pay each other for work. They're used by a common set of outside users. Of course, you can have AI agents in the network spawn new AI agents. I mean, the trivial example would be a model learning agent spawning different deep learning models, but it could get a lot subtler than that. Like you could have an OpenCog agent spawn other OpenCogs doing speculative learning on different knowledge bases and so forth. So AIs can create new AIs, which sounds fancy, but everyone here understands it's not really the hardest part. And there's an Internet of Things application as well, which is interesting from an application standpoint. So I mean, you can put a SingularityNet node, in your toaster, in your pacemaker, in your brain implant, your thermostat, your car, whatever. And this is interesting in the same way that the Hanson Robotics stuff is interesting. It gives a variety of sensors and actuators to feed into your AI. And I mean, this is one of the big lessons of the deep learning revolution in the last few years, is data is really important and interesting for your AI. I mean, ultimately we need the right algorithms like the inference meta learning I was discussing earlier, but you also need to be doing the right things with those algorithms in the early stages to bootstrap things. And so having something like SingularityNet, which has different AI agents doing pre-processing and analysis of data from all sorts of embedded devices and computer programs, having this sort of simpler level of sensory data processing AI in there, along with more abstract AI doing things like inference meta learning, and having all these AIs connected in some loosely connected network like SingularityNet. I think that's a network, that's the direction that we need to go in. So we're building the Singularity Net platform now. I mean, we're somewhere, we have had an alpha in GitHub for a while. we're working toward the beta now, and different components will reach beta at different points in the next 6 or so months. We're lining up various corporate partners to use this network for their internal AI needs, and in the open source and blockchain community spirit, we're recruiting more and more volunteer developers, and we're offering token bounties for people doing development. And we're hoping that 2019 will be the big growth year for this in terms of beginning to get real utilization of this marketplace. So yeah, I'm so optimistic that my friend Ray Kurzweil's date of 2045 for the singularity will be met, or hopefully we can get there first. And you remember now, Ray said we're going to get to human level AI by 2029. And I never understood why he put 16 years between human level AI and the singularity, because I think once you get human level AI, you can replicate that human level AI a million times. The human level AI can be taught computer science and can refactor its own representations. I'm figuring from an AI as smart as someone in this room to a singularity is at most years, not 16 years, maybe even months. 2029 for human level AI, maybe that's only like 11 years from now, but I'm hoping we can beat Ray by a couple years anyway. So we're aiming for 2025 or something, just to be sure we get there before Ray and Google do. Now, I have two minutes left. I don't have time to do full justice to the topic of AI ethics, but I want to say a little bit about my approach to that. And we've seen the big tech companies of the world make very interesting noises about this in the last few years. And the history of Elon Musk, who is one of my heroes and an awesome guy, but the history of his thoughts about AI ethics has been interesting, because Elon, I'm sorry. By the way, I'm shorting your stock. All right, so 2014, Elon Musk sounded an alarm that AI researchers are summoning the demon and you can't put it back in the bottle. 2015, there's a sort of soft commitment of up to $1 billion to OpenAI, which is a great program doing really awesome neural net development for beneficial AI development. 2017, some of the top folks from OpenAI have gone to Tesla to do practical computer vision work for Tesla. And I don't see anything wrong here. What I see here is a movement from, well, AI is big and scary and we don't understand it. It could be bad, to, well, we need AI to do like useful things right now. Like there's an ethical issue of cars running people over or crashing. Let's solve that ethical issue with AI right now, rather than worrying about hypothetical ethical issues to an excessive degree. And a more humorous thing was Google removing "Don't be evil" from their code of conduct, which, I mean, doesn't matter a lot. No one reads the code of conduct of a big company when they go to work there anyway. But of course, if we really want to create a positive singularity, as Ray Kurzweil and the Google founders and Elon Musk and probably almost everyone in this room wants to do, I mean, "Don't be evil" isn't good enough, right? I mean, we actually want to do good, and that's why I'm applying AI to things like helping people meditate and things like analyzing biology data, rather than making killer robots or surveillance or advertising engines. So I think as we build these networks of networks of networks and insert our intelligent algorithms within them, it's important to bias these AIs toward positive things. And I don't want to minimize the importance of work thinking explicitly about, like, how do you code goodness into your algorithm, and what's the mathematics of ethics, and how can AIs preserve their goal system under self-modification. All these more formal approaches to AI ethics are interesting. I'm glad people are working on them, but I think we also want to pay attention to real-world AI ethics right now, as Elon Musk is doing with applying computer vision to make cars not run into people. And as we develop toward real-world AGI. Let's make sure the AGIs we're developing are doing useful and helpful things for people, rather than malevolent or merely non-evil things. And this has been one of the motivations behind SingularityNet and its decentralized and democratic aspect. Because I would rather not see AGI developed within a military organization or in a proprietary and secret way inside a large corporation. I mean, that could come out for the best, and if it does, I'll be really happy, but my bias is I would rather see AGI come about in like an open, democratic, and participatory way, where maybe 50 people in this room each put some AI algorithm online, and they're cooperating with each other to create emergent general intelligence, and it's being applied to things that are helping people all around the world as it grows. And that would really be, in my view, the scenario most likely to lead to a beneficial singularity, as Kurzweil and others have predicted. And it's very exciting to be alive at a time when we can really be working on building complex networks on all these layers, moving toward general intelligence. Thank you.